In this video, we're gonna solve the time-dependent Schrodinger equation. It's equation number 1. And then we're gonna solve the time part of this equation. Once and for all, we solve the time part of it and we are done. From there, we're gonna convert it to spherical coordinates. And then we're gonna use separation of variables to solve it. We're gonna get two equations from it, the angular equation and the radial equation. We're gonna use Legendre polynomials to solve the angular equation, and then we're gonna use Legendre polynomials to solve the radial equation. At the end, we're gonna arrive to this bottom equation. This is the solution for the time-independent Schrodinger equation given by Legendre polynomials. These are these guys over here, and these polynomials and Legendre polynomials, the ones right over here. The Schrodinger equation reads I h bar times the time derivative of the wave function, and now I'm gonna put big psi, okay, because we're gonna look at the time dependent Schrodinger equation, equals the Hamiltonian times psi back, and the Hamiltonian is given by the kinetic energy 1/2 m velocity square plus some potential function v. And if you remember, the velocity is nothing but the first derivative. So if we look at if we defined few variables, let's define the p of x as h bar over I times the partial time x derivative, p of y in the same manner but in the y axis, and p of z is h bar over I times the partial derivative with respect to the z axis. So in terms of these p's, the Hamiltonian reads 1 over 2m times p sub x square plus p sub y square plus p sub z square plus the potential function. Up to this point, we don't know what the potential function is, okay? But remember, we're doing this for the hydrogen atom. And up to this point, we're doing this in Cartesian coordinates, okay? As you see, we have x, y, and z. Let's remind ourselves of the Laplacian. So the Laplacian reads nebula square, this thing here called nebula. Nebula square, or the Laplacian, in Cartesian coordinates is defined as the second partial derivative with respect to x plus the second partial derivative with respect to y plus the second partial derivative with respect to z. So this is the Laplacian in Cartesian coordinates. So our Schrodinger equation in terms of the Laplacian reads I h bar times the time derivative, the partial time derivative of psi equals minus h bar squared divided by 2m times nebula square times psi plus some potential function times psi back. So this is the Schrodinger equation in terms of the Laplacian in Cartesian coordinates. So now we're gonna try to solve this equation, to solve the time part of this equation. As you can know, if we just assume a solution and we try it into the equation, if we assume a solution and it works, then good, we're just gonna take it. So we're gonna assume that the solution, the wave function psi, it contains some states we don't know. Let's call it psi sub n of both position and time. This is the wave function. It's both in position and time, is equal to some other wave function psi we don't know, that is only in position, times the time part of it, and the time part of it is e to the minus I e sub n times time divided by h bar. So if you look back at the Schrodinger equation, so this is the solution for the time derivative, I mean for the time part. The Schrodinger equation reads IH bar, that the time derivative of psi equals minus h bar squared divided by 2m times nebula square times psi plus some potential function times psi. If you take the solution, this part here, let's call it equation number, okay, let's call it number 1. So if you take equation number 1 and plug it back into equation number 2, this one here, you're gonna see that it works. Let's take a one-time derivative here. This generates minus I e sub n divided by h bar, okay, and times this, times the exponential part, it's gonna give this back. And if you put this here, you're gonna get the same stuff. So just try it and plug it in and see how it works. So that's it. This is the solution for the time dependent Schrodinger equation. Of course, it's missing this piece here because we don't know. But this is what we're gonna find next. But for now, we solve the time part of the Schrodinger equation. So now we come to the time independent Schrodinger equation, which goes to minus h bar squared divided by 2m times the Laplacian times psi back. This is a small psi now, so this is the same thing as this psi with the 3 lines underneath, plus some v times psi, okay, equals e times psi. This comes from the solution here. So let's call this equation number 3. So equation number 3 is the time independent Schrodinger equation. Up to this point, we don't know what's the potential function v, so we can't solve it. But we can arrange to solve it, okay? So let's do that. First of all, as you know, the Laplacian, this guy here, is in Cartesian coordinates. And this v, the potential function, potential O is a function of distance, right? So the potential function is also is a function of distance. So r is just a vector. In terms of x, y, and z, this potential function have x, y, and z. So it's a function of 3 variables. This Laplacian also a function of x, y, and z. It turns out if you switch your coordinates from Cartesian to spherical coordinates, things gonna get a lot easier. Why? Because if you switch to spherical coordinates, your potential function is only a function of one variable r. But in order to do this, you have to change the Laplacian to spherical Laplacian. So spherical Laplacian, let me erase this. So the Laplacian in spherical coordinates is given by 1 divided by r squared times the partial derivative with respect to r times r squared times another partial derivative with respect to r plus, so this has 3 pieces, okay? The first piece only in terms of r, the second piece is in terms of both r and theta, sine of theta times a partial derivative with respect to theta times the sine of theta times a partial derivative with respect to theta. So this is the second piece, and the third piece is in terms of both, I mean all 3 variables, is 1 divided by r squared sine square theta times the second partial derivative with respect to phi. So now we switch our Laplacian from Cartesian x, y, and z to spherical r, theta, and phi. So in terms in spherical coordinates, our Schrodinger equation reads minus h bar square divided by 2m times the Laplacian in spherical coordinates. So just take this Laplacian. This is a function of r, theta, and phi. Okay, yeah, plus our potential function. Now our potential function is only a function of r. Before it was a function of x, y, and z. So, plus the potential function equals E times psi. Yeah. Oh, of course there's psi here and psi here. I forgot these. So let's call this what equation number what? Let's call this equation number 4. So our job is to solve for this psi. Our job is to find the wave function for this psi. So I'm gonna assume the solution. So psi is a function of r, theta, and phi now. I claim the solution is a function r and another function y, theta and phi. So I assume that our wave function psi is the product of two other functions, r and y. The r function is a variable of only r, and the y function is a variable of theta and phi. So with this assumption, we can take the solution and plug it back into equation number 4. So, but before we do this, I'm gonna draw my coordinates here so we can have imagination of what's going on. So this is the y-axis. This is the z-axis. This is the x-axis. So our electron is here, and the origin, the center of this drawing is the nucleus. Remember, we're doing the hydrogen atom. So if our electron is here, let me see. We can drop a line to the xy plane, and this is going to be something like that. So from the center, from the origin to the electron, this is the r. Okay, and let me connect these two here. The angle from the x-axis to this line, this is theta. So, and the angle from the z-axis to the vector r, this angle is oh no, sorry, this angle is theta and this angle is phi. Okay, so this angle is phi from the x to this dotted line. This angle is phi. From the z-axis to the r, this angle is theta. And this is the point. Okay, so now we're gonna take our solution, psi equals r times y, and we're gonna plug it back into equation number 4. So when we do this, we get minus h bar square divided by 2m times y, because y is a function of theta and phi, so we're just gonna put it outside, divide by r square, the derivative with respect to r of r square times dr Remember, this r function is a function of r. So plus r divided by r squared sine of theta times the partial derivative of theta times sine of theta times the partial derivative of y with respect to theta, and the third piece plus r divided by r squared sine squared of theta times the partial derivative with respect to phi of y plus v is the potential function times r times y equals e times psi, but psi is r times y. Let's call this equation number 5. Okay, so now we're gonna arrange few things. So dividing by ry and then multiplying by minus 2m r squared divided by h bar squared. So first we're going to divide this entire equation, equation number 5. We're going to divide it by ry and then we're going to multiply by this quantity here. So when we do this, we get 1 divided by r times d dr of r squared dr minus 2m r squared divided by h bar squared times v of r minus e. So this is one part plus 1 divided by y times 1 divided by sine of theta times the partial derivative with respect to theta of sine of theta times the partial derivative of y with respect to theta plus 1 divided by sine square of theta times the second partial derivative of y with respect to phi. This equals to 0. Let's call this big equation equation number 6. The reason we did this is a method. This method is called separation of variables. So we separated the r variable, this is the first piece here, okay, from the angles variable, which is the y. Y is in terms of theta and phi. So now, since we separated equation number 5 into 2 terms, each term is in different variable, it will be easier for us to solve, and you're gonna see why in a minute. Separation of variables is the most effective way to solve differential equations, and it's our first weapon of attack. We see a differential equation, we think separation of variables. So you see here equation number 6 is in terms of 2 terms. The first term, the one right over here, and then the second term. And if these 2 terms, the sum of them equal to 0, this means that we can give them variables. So we can call this the first term, the one with the red line underneath, we can call it x, as long as we call the other one minus x, because x minus x equal to 0. Or we can call the first part, the first term here, we can call it like dog, as long as we call the second part dog, then dog minus dog equals 0. So we're gonna call this okay. So we're gonna say 1 divided by r, this is the first part, times ddr times r squared dr plus, minus 2mr squared divided by h bar squared times v of r minus e. We're gonna call this, let's call it L times L plus 1. We can do that. What equation? Equation number 7. So let's give it a number. This equation number 7. We can do this as long as we call equation number 8 the opposite of this. And equation number 8 is 1 divided by y times 1 divided by sine of theta times the partial derivative of with respect to theta of sine of theta times dy, the partial derivative of y with respect to theta, plus 1 divided by sine square of theta times the second partial derivative of y with respect to phi. This must equal minus L times L plus 1. So now we have two equations, equation number 7 and equation number 8. And we're gonna solve them individually. We can't really solve equation number 7 until we have a potential function, because this function we don't know how it behaves. Until we know how it behaves, we can't solve this equation. So right now we're just gonna focus at equation number 8. We're gonna try to solve this equation and find out what y is. We're gonna use separation of variables to solve equation number 8. But before that, let's try to rearrange this equation a little bit. So by multiplying the equation number 8 by y sine squared theta, we get sine of theta times the partial derivative with respect to theta of sine of theta, the partial derivative of y with respect to theta, plus the second partial derivative of y with respect to phi equals minus L times L plus 1 times sine square of theta times y. Alright, so we're gonna assume the solution y, remember y is a function of theta and phi. We're gonna assume y to be the first function theta of theta times phi of phi. So this is our solution, and now we're gonna take it back and plug it into equation number 8, or basically let's call this equation number 9. So we're gonna take this solution, plug it back into equation number 9, and we're also gonna divide by theta phi. So when we do this, we get 1 divided by theta, this is the function, times sine of theta d theta d theta times sine of theta d theta plus L times L plus 1 times sine square of theta. So this is the first piece, plus 1 divided by phi, this is big phi, times the second derivative of phi with respect to phi. This equals to 0. Let's call this equation equation number 10. So now we have this equation number 10 is made in is made in terms of two terms. The first term, the theta term, and the phi term. And if these two things added to 0, this means that we can assign a constant to each one that adds up to 0. And we're gonna do that. We're gonna assume the constant is minus m squared. You may say, I'm not gonna come up with this on your own. That's fine. You can assume C1 if you want the constant, but after a while you're gonna find out that if you assume the constant to be minus m squared, things gonna get a lot easier. But that's fine. If you wanna call it something else, call it whatever you want. So this is the first equation, the theta equation, d theta plus L times L plus 1 times sine square theta. This we're gonna assign the constants m square, and we're gonna call this equation number 11. And the second equation, equation number 12, will be 1 divided by phi times the second derivative of phi with respect to phi. This must be equal minus m square. There you have it. We have two equations. We can solve each one individually. Equation number 12 is easy, right? This is just the wave function, and we know the solution for this equation. So multiplying both sides by theta, we get a theta here, and this disappears, right? Okay, so now the solution for this guy is theta of theta is equal some constant, we're not gonna worry about it right now, times e to the I m theta. This is small theta. There's also the negative solution where the solution is equal to e to the minus I m theta, but that's fine. We're gonna account for this by allowing m to run from negative to positive. If you remember, we assign this is the point in space. If you remember, we assign phi to be this angle here. So if this is the point or the electron and this is phi, if you start here and added 2 pi to it, you come back to the same place in space, which means that theta of phi plus 2 pi is the same thing as phi of phi, right? So if you start at the angle, if you start at some value of phi and you add 2 pi to it, you get to the same place. Which means, in other words, before this, let's call this equation number 13. And in other words, mathematically we have e to the I times m times phi plus 2 pi. This should be equal to e to the I m phi, right? Or e to the 2 pi I m equals 1. This formula here tells us that m must be an integer. So the values of m goes like, it can be 0, it can be plus or minus 1, it can be plus or minus 2, plus or minus 3, and so forth. Okay, so we're done with equation number 12. We solved it. So this is the solution for the theta, for the phi angle. Now we're gonna try to solve equation number 11. It turns out that equation number 11 is not that easy. So we're gonna assume the solution, and you're gonna say, how did you assume a solution like this? This is the job for the mathematicians. I'm gonna post a link. If you wanna see how this is done, you can go there, but we're not gonna actually do the derivation in here. It's probably gonna take us like two hours to do that. So I'm just gonna go ahead and assume the solution for equation number 11. So let's rearrange few things. Okay, this is the Theta equation. So we're gonna rewrite it as sine of theta d theta of sine of theta d theta plus L times L plus 1 times sine square of theta minus m square times theta equals 0. What equation? This is equation number 14. So we're gonna call this equation number 14. Not so simple. This equation is called the Laplacian equation in spherical coordinates. The solution for this guy is theta of theta equals some constant a times p sub L to the m power of cosine of theta. And these guys called the associated Legendre functions. Associated So the associated Legendre functions defined by P of L and M are given by this following formula, where P of L and M of cosine of theta is equal to minus 1 to the m, this is the same m power, times sine of theta to the m power times the mth derivative with respect to cosine of theta times the Legendre polynomials of cosine of theta. Okay, so by looking at this equation, let's call it equation number 15, you can see we're taking the nth derivative of some polynomial in the nth order, which means if L is 3, M cannot be bigger than L. It has to be less than or equal to L in order to make sense. So because if, like, let's say L is 3 and M is 4, then we're taking the fourth derivative of a third order polynomial, and that's going to be 0, so this cannot be possible. So this allows us to say that M has to be less than or equal to L. Alright, and P of L of X, this is the Legendre functions, the Legendre polynomials given by the Legrege's formula, is defined as some coefficient 1 divided by 2 to the Lth times L factorial times the Lth derivative of X times X square minus 1 to the Lth power. This is in terms of cosine of theta. This is just the Legrege's formula is in terms of X, but you can substitute cosine of theta for X. It's going to be basically the same thing. So this is the solution for equation number 14. Equation number 15 is the associated Legendre functions. These give solutions to the theta part of the Schrodinger equation for the hydrogen atom. Let's take a look at the first few terms of the associated Legendre polynomials. So we have P, let's go back to that color. We have P of 0 and 0, where L is 0 and M is 0, of cosine of theta. This gives you 1. Now you have P, well, L is 1 and M is 0, of cosine of theta. This equals to cosine of theta. Now if you have P of 1 and 1, this gives you minus sine of theta. P of 2 and 0, this gives you 1/2 times 3 cosine square of theta minus 1, and so forth. You can look them up if you want. Just you can make a search of associated Legendre polynomials. Let's draw the first few of the associated Legendre polynomials. So this is P 0 and 0. It's just going to be a circle, right? And if we're going to draw P 1 and 1, it's going to be 2 circles like that. And if we draw a few more, so P, L equal 1, M equals 0, it's gonna look 2 circles in the, this is the z-axis. Alright, and if we draw P 2 and 1, it's gonna look something like that. Also here. P 2 and 0. It's gonna look something like that. Right? I hope these look familiar from chemistry 1, if you remember how these atomic orbitals look like. This is P, L equals 2, M equals 2, looks something like that. So that's how we know how these atomic orbitals look like from the Schrodinger equation. Let's carry on. Let's remind ourselves of an infinitesimal region in 3 dimension. This looks this equals to r square sine of theta times dr d theta d phi. Correct? Why I'm mentioning this? Because we're gonna try to normalize the solution we just got for the associated Legendre polynomials. So if we integrate, we're gonna integrate psi, the probability density, which is psi star psi, or psi square. So psi star psi square times r square times sine of theta dr d theta d phi. And psi is made out of 2 functions, right? It's made out of the r function r square dr times the y function times sine of theta d theta d phi. As you can see, these 2 integrals are multiplied, so their product must equal to 1. This is what normalization is, remember? So it's best if we integrate these separately. So we're gonna integrate the r from 0 to infinity, of course. r star r times r square times dr. This equals to 1. And these are gonna have 2 integrals, right? The first integral is gonna be from 0 to pi, and then the second integral is gonna be from 0 to 2 pi. The first integral gonna be the theta integral. They both have y star y times sine of theta d theta. That's the first integral from 0 to pi, and the second integral is going to be from 0 to 2 pi. This is the phi angle, and this integral also equals to 1 because their product has to be equal to 1. So 1 times 1 is 1, of course. The reason we're doing this integration again is to find the normalization factor for our y functions. I'm gonna do this in a separate video. It's not easy, it's quite hard, so I invite you to do it on your own. If you can't, I'm gonna attach a link on how to find the normalization factor for the y solution for the Schrodinger equation for the hydrogen atom, or the isothermal equation, or the angle equation. This is going to equal to epsilon, this comes from normalization, times the square root of 2l plus 1 divided by 4 pi. You can see where the 4 pi came from, times we have L minus absolute value of m divided by L plus the absolute value of m, and these are factorials. So that's all square root here. times e to the I m phi, this is our phi angle solution, times our associated Legendre polynomials times cosine of theta. There you have it. So this is equation number, this is the solution for the second half of the Schrodinger equation. And let's see, what number is this? This is equation number, let me see. This is going to be equation number 16. There you have it. So these are the solutions for the azimuth part of the Schrodinger equation for the hydrogen atom. I also want to say that epsilon is equal to -1 to the m power for m greater than or equal to 0, and epsilon is equal to 1 for m is less than or equal to 0. There you have it. This is the solution for the Schrodinger equation, the first half of the equation. I also want to mention that these solutions are orthogonal to each other, in the sense that if you integrate y of L and M star, or complex conjugate, times y L and M times sine of theta d theta d phi from 0 to pi, from 0 to 2 pi. If you integrate this equal to Kronecker delta, if you remember this from the first videos, Kronecker delta of L prime and Kronecker delta of M and M prime. My bad, this is L prime and M prime. So when the L equals to L prime, Kronecker delta equals 1, and when M equals M prime, Kronecker delta equals 1. Otherwise, they both equal to 0. For historical reasons, we named these variables. We named the L the azimuthal quantum number, and the M, we named it the magnetic quantum number. Okay, so now we know what L and M are. We are done with this half of the Schrodinger equation. Now we're gonna tackle the second half, which is the radial equation. So the radial equation, if you remember, this is equation number 7, if I recall correctly. So we have the ddr of r square dr minus 2 times mass times r squared divided by h bar square times some potential function, it's a function of r, minus energy E times R. This equals to L times L plus 1 times R. Alright, we're gonna induce a new variable. It's gonna make our life a lot easier. It's gonna make us see things more clearly. So we're gonna induce this new function, u of R. And we're gonna define it as R times big R of R. Which means that if I'm solving for R, I get R equals U divided by R, right? So let's take two derivatives of this R. So dr equals R du dr minus U divided by R squared. The reason I'm gonna take two derivatives because I have here one derivative and then I'm taking another derivative of it, so I need that. So let's take another derivative of this guy. So ddr of, let's do this, r squared dr. So let's take this and let's substitute this piece here in here and see what we're gonna get. We're gonna get r the second derivative of u with respect to r. So now we have all the pieces. So let's try to rewrite equation number 17 in a different form. Okay, so now we have minus h bar squared divided by 2m times du, I mean the second derivative of u with respect to r, plus some potential function v plus h bar squared divided by 2m times L plus 1 divided by r squared times u equals e times u. So this guy gonna be our equation number 18. So this is the equation we're gonna solve. We're gonna try to solve for u of r. Up to this moment, we don't know what our potential function. We don't know what our potential function is. This guy here. So for the hydrogen atom, the potential energy we have is just the Coulomb force, and we know what the Coulomb force is. So we have V of r is equal to minus the charge of the electron square divided by 4 pi epsilon naught times 1 divided by r. So this is our potential function. Let's plug it into equation number 18 and try to solve it, okay? So now we have minus h bar squared divided by 2m times the second derivative of u with respect to r plus our potential function, which is minus e squared divided by 4 pi epsilon naught, this is just a constant, times 1 divided by r plus h bar squared divided by 2m times L plus 1 divided by r squared. This is going to be times u equals e times u. This is equation number 19. Alright, this is not so easy to solve. So we're going to approach a new method. Okay, we're going to use the method, the analytical method of solving this equation, just like the harmonic oscillator. So, but before this, let's make it a little bit easier. Let's induce another variable k to make things a lot cleaner. K gonna equal to square root of minus 2 times mass times E divided by h bar. So we're gonna take equation number 19 and divide by k. Okay, so let's try to do that. When we do this, we get 1 divided by k squared du with respect to r, the second derivative, is going to be equal to 1 minus me squared divided by 2 pi epsilon naught h bar times k times 1 divided by k times r plus L times L plus 1 divided by k times r parentheses square. I'm skipping a lot of algebra, by the way, okay? So this is just, but you can trust my work. I invite you to do the algebra every step of the way, but if I want to do it, it's probably going to take me 10 hours. So I'm just going to try to put the big bullets equations. So let's try to clean things up. I'm going to introduce two more variables. Rho, I'm going to define it as k times r, and rho naught, I'm going to define rho naught as m e squared divided by 2 pi times epsilon naught times h bar square times k. Alright, with this new, let's call this equation number 20. With this new variables, we're going to plug them into equation number 20. We're going to have a very clean equation. So we're going to have the second derivative of u with respect to rho, because now rho has r in it, okay, equals 1 minus rho naught, which is a constant, divided by rho, plus L times L plus 1 divided by rho square times u. Let's call this equation number 21. Okay, so now we have to solve equation number 21. It looks a lot cleaner, so we can look at it and understand a few things. Let's take the limit. Let's take the limit as rho approaches infinity. If rho approaches infinity, this term gonna equal to 0, and this term gonna go to 0, which gonna induce equation number 21 to a simpler one, only in this limit though, okay? So keep this in mind. With this being said, we have second derivative of u with respect to rho is equal to 1 times u, right? Which is just u. Yay, this is a very easy differential equation. We know the solution for this guy. The solution is u of rho equals a times e to the minus rho plus b times e to the rho. But we took the limit as rho goes to infinity, so this makes this our second term, the b term, blow up, and we can't do that, so we have to set b equal to 0. B equal to 0. So if b equals 0, our solution u of rho is approximately equal a times e to the minus rho. You may say, oh, this is very like smudgy work. We didn't really solve the true equation number 21, but we didn't. No, we didn't. We only solved equation number 21 only in one limit, when rho is very, very, very large. So now we're gonna take a look at as rho approaches 0. As rho approaches 0, let's take a look at the equation number 21. I'm gonna put it here in the box. We have the second derivative. Let's write u double prime. The second derivative equals 1 minus rho naught divided by rho plus some l's here, right, divided by rho square times u. Right, this is equation number 21. So as rho goes to 0, the third term, this term gonna dominate, correct? Because it's on the bottom, so it's gonna increase very rapidly, which gonna make our equation number 21, it's gonna look something like this. It's gonna look the second derivative of u with respect to rho equals L times L plus 1 divided by rho square times u. Let's call this equation number 22. And we know the solution for this equation. The solution for this guy is u of rho equals c times rho to the L plus 1 plus d to the rho d times rho to the minus L. So this is solution for equation number 22. Check it and see if it works. But remember, we took the limit when rho goes to 0, and we can't let this happen over here. So because it's going to be at the bottom, remember, this is this negative, gonna put the whole thing at the bottom. So we have to make d equal 0. Okay, which gives us the solution u of rho equals c times rho of L plus 1. Alright, you may say, okay, this is still not done. We didn't find the whole solution. We didn't know the function u, but we know the function at its upper limit, infinity, and it's at its lower limit, 0. So we're gonna hope that there's a function somewhere in between that we're gonna try to find in a minute. So let's assume this function. Let's assume the solution u of rho equals rho of L plus 1. Ignore the constants. These are just normalization constants. This is the zero behavior. And we have the infinite behavior. It's e to the minus rho. And we're gonna induce a new function, nu of rho, that's gonna take care of the rest. Let's call this equation number 23. Okay, so we're gonna try to take one derivative. Let's take a derivative of equation number 23. So d of u d rho is gonna equal to rho to the L times e to the minus rho times L plus 1 minus rho times nu plus rho times d nu d rho. Okay, so this is one derivative. Let's take another derivative, because equation number 20, I think it was equation number 20, the equation we're trying to solve has both the first derivative and the second derivative. So we're gonna try to do the second derivative, d. So second derivative of u with respect to rho, that's gonna equal to rho to the L e to the minus rho times, we have minus 2L minus 2 plus rho plus L times L plus 1 divided by rho. It's going to be times nu plus, we have 2 times L plus 1 minus rho times d nu d rho plus rho times the second derivative of nu with respect to rho, close bracket. Okay, so that's the second derivative. We're gonna take these two and plug them back into the radial equation, the equation we started with. So once we do this, we're gonna get rho times the second derivative of nu with respect to rho plus 2 L plus 1 minus rho d nu d rho plus rho naught minus 2 times L plus 1 times nu. This is gonna equal to 0. Let's give it a number. What number are we at? 24. So this is equation number 24. Our job now is to solve for the new function nu of rho. If we find nu of rho, we are done. So I'm gonna claim the solution to be a power series. Okay, so this is gonna be, I'm gonna assume the solution to be nu of rho equal the sum of some index, some dummy index j, starting from 0 all the way to infinity, of c of j, some constant, times rho of j. And if it works, good. If it doesn't work, we have to try something else. So this is nu. In order to see if this equation is true, we're gonna have to take one derivative and also take a second derivative and plug them back into this equation, equation number 24. If this equals to 0, you got it. Your assumption is correct. Of course, there might be other solutions, and they are, but these solutions don't make any physical sense. Taking one row derivative of nu, we get d nu d rho equals the sum when j starts from 0 to infinity of j times c sub j times rho times j minus 1. So I'm gonna rename the dummy variable j. I'm gonna call it j plus 1. So now we have the sum when j starts from 0. Few objects on why the j now starts from 0. It should start from -1. That's good. Write the first term and see what the first term gives you. So this is gonna give us j plus 1 times c sub j plus 1 times rho to the j. Taking another row derivative of nu, we have the second derivative of rho with respect to nu equals the sum when j starts from 0 to infinity of j times j plus 1 times c sub j plus 1 times rho to the j minus 1. Inserting these two back into equation number 24, we get the sum when j starts from 0 to infinity of j times j plus 1, this is the second derivative, times c sub j plus 1 times rho to the j power plus 2 times L plus 1 times the sum j starts from 0 to infinity j plus 1 times c sub j times rho to the j minus 2 times the sum j starts from 0 to infinity times j c sub j rho to the j plus rho naught minus 2 times L plus 1 times the sum when j starts from 0 to infinity of c sub j rho to the j power. This equals to 0. And let's call this equation number 25. Okay, so putting like powers together, we get j times j plus 1 times c sub j plus 1 plus 2 times L plus 1 times j plus 1 times c to sub j plus 1 minus 2 times j times c sub j plus rho naught minus 2 to the L times L plus 1 times c sub j. This equals to 0. Let's try to take this last equation and solve for c sub j plus 1. So let's go ahead and do that. When we do this, we get c sub j plus 1 equals 2 times j plus L plus 1 minus rho naught divided by j plus 1 times j plus 2 L plus 2 times c sub j. This is a very important formula here we got to. This is the recursion formula. This is it. Let's call it equation number 26. The recursion formula. Okay, so this is the formula, and let's take the limit for large j. We have c sub j plus 1 approximately equal to 2 times j divided by j times j plus 1, which is equal to 2 divided by j plus 1, right, times c sub j. Forgot it here. Okay, which means that c sub j is equal to 2 to the j divided by j factorial times c naught. This is the first term. This is the first c naught in the term. So with this being said, let's carry on. So now we have, for large j, we have nu of rho is equal to c naught, the sum when j starts from 0 to infinity of 2 to the j divided by j factorial times rho to the j, which is the same as c naught times e to the 2 rho. If you remember from calculus 2, if you remember this formula, that e to the x, we can write it as a power series and start from 0 to infinity of x to the n divided by n factorial. So we use this formula here. For large j, which is the same as saying large rho, we have the function we're trying to solve for, the u function. U of rho is equal to c naught e to the rho times rho to the L plus 1. But this is exactly the behavior that we didn't want. For large j, which is the same as large rho, this function gonna blow up, and this is exactly what we don't want. This tells us that there must be a maximum j where this equal to 0. So there must be some constant times J max, let's call it max J, J max plus 1. This must be equal to 0. Let's clean this up. So this tells us that 2 times J sub max plus L plus 1 minus rho naught, this has to be equal to 0. This is the top part of equation number 25. 26, I mean, the recursion formula. So the top part of the equation number 26 must be equal to 0. Let's take this guy. Let's give it a variable. Let's call it n. So we're gonna define n as J max plus L plus 1. And this n number, there's a name for it. I mean, this n variable. Can you guess what's this called? It's called the principal quantum number. Here we go. So we have the n. We defined it as the maximum value of J plus L plus 1, and we call this n the principal quantum number. Let's call this equation number 27, because we're gonna refer to it. And let's do some algebra. 2n minus rho naught equals 0, which follows that rho naught equals 2n. Let's call this equation number 28. And if you recall from earlier, we called rho naught something in terms of k, and we called k something in terms of e. So going back to these equations and solve for e, we get e to be equals to minus h bar square divided by 2m times k square, which means that we have minus m e to the 4th divided by 8 pi square epsilon naught square h bar square rho naught square. But rho naught is equals to 2n, so we can rewrite this e sub n now, because we're going to make the substitution. We have e equals to minus some constant, I hope this looks familiar, divided by 2 h bar square times e square divided by 4 pi epsilon naught parentheses square times 1 divided by n square. We took this whole constant, okay, and we give it a variable. We call it E1. It's actually a number. Can you remember what this number is? E1 divided by n squared. I'm sure you remember this formula from chemistry 1. You know, the energy levels for the hydrogen atom goes as this constant. I hope you remember what this number is, divided by n squared. So if n equals 1, it's just E1. If n equals 2, it's E1 divided by 4. You'll see in a minute what this constant is. It's actually really cool how we can arrive to this constant without without any experiments, but this constant has been verified by experiments and empirical evidence. So n runs from 1 to 2 to 3 and so forth. Okay, so now we're gonna combine two equations and put them together, and we'll arrive to the second constant, very popular one too. If you recall, we have rho naught. We defined it as m e squared divided by 2 pi epsilon naught h bar squared times k, and we also have rho naught equals to 2n. Combining these two equations, we get k to be equals to m e squared divided by 4 pi epsilon naught h bar squared times 1 divided by n squared. We took the reciprocal of this constant and we give it a name. We called it a. So let's define a together. I hope this looks familiar. This is chemistry 1 stuff. A equals 4 just from this constant, 4 times pi times epsilon naught times h bar squared divided by m e squared. Taking these constants and plug them in, you get 0.529 times 10 to the negative 10. What's the unit? Meters. I'm very sure you know what this constant is right now. This constant is the Bohr radius. Beautiful. So we arrived to the Bohr radius without going to the lab, just from sitting here and solving the Schrodinger equation for the hydrogen atom. And this number has been verified by experiment, so this is, we should celebrate, you know. Alright, so from this equation, let's carry on. From the equation, we defined rho as k times r, remember? So now in terms of a and n, rho is equal to r divided by a times n. So there you have it. Now we have rho. If you remember, we tried to solve for psi. This is like the dream, right? So we have psi sub n, l, and m. It's a function of r, theta, and phi. And psi is made out of two functions. It's made out of r sub n and l, and it's made out of the function y sub l and m, theta and phi. Okay, so this is that. From earlier equation, we defined the u of r. We're trying to put everything together now. U of r as r times r of r, right? And we defined the u of rho to be equal to rho times L plus 1 times e to the minus rho times this new functions of rho, right? So r of n and l is now equals to 1 divided by r times rho to the l plus 1 e to the minus rho times these functions nu of rho. Let's give this equation a number. Let's give it equation number 31. Okay, so now let's take a look at these equations. These are equations, polynomials of degree j max, yeah? So these are polynomials of degree j max, which is equal to n minus L minus 1. So now we're gonna rewrite the recursion formula, equation number 26. We're gonna write it in terms of n. So now we have Cj plus 1 equals 2 times j plus L plus 1 minus n divided by j plus 1 times j plus 2 L plus 2 times C sub j. So this is equation number 32. It's also the recursion formula. Alright, so let's go back. Keep this in mind. This is going to be very important in determining the nu of rows, these functions. We determine these functions by this formula. But let's go back a minute and give you what E1 is. We defined it as m times a constant, the mass of the electron, right, divided by 2 times Planck's constant square times the charge of the electron square divided by 4 pi epsilon naught parentheses square. Take these numbers and plug them in. You get a very unique value, negative 13.6 electron volt. This is the amount of energy required to knock off an electron from its orbit for the hydrogen atom. So it's very unique. We can look at the Schrodinger equation and know what's the ionization energy for hydrogen. If we solve the Schrodinger equation for the helium atom, which we're gonna do in future videos, we're gonna find the ionization energy for helium. This is identical to experiment for the hydrogen. For the helium, it's gonna be very close approximation. You will see in the future videos. And if you take this and divide it by n square, where n is equal to 2, for example, you're just gonna take this divide by 4, and you're gonna get what? Negative 3.4, right? This is the ionization energy for the hydrogen atom in the exciting state. So this works. The Schrodinger equation works. Alright, so if this energy for n equals 1, right? So if n equals 1, this forces L to be equal to 0. Because if you remember the equation, where is it? I think we defined n as like L plus J plus 1, I think. Let me just double check. Yeah, so we defined this as J max, right? So if n equals 1, J max must equal 0 and L must equal 0 for this equation to be true. Alright, with this in mind, this gives us the first quantum state when n equals 1 and L equals 0 and M must equal 0, because if you remember, we defined it M must be less than or equal to L. If L is 0, M must be equal to 0. So, alright, so now we have the first quantum state for the hydrogen atom. It's made out of two functions, r of 1 and 0 of r times y of 0 and 0 of theta and phi. Okay, let's move on a little bit further. R of 1 and 0, what is that? This is equal to C naught, some constant, we don't know, we're going to determine by normalization, times A, right? A times n plus n squared, but n is equal to 1, so that's just 1. E to the minus R divided by A, right? So let's determine this constant C naught by normalizing this. So we're going to integrate from 0 to infinity R star R, right? Times R squared. This R squared comes from the dr factor because we're working in spherical coordinates. This equal to C naught squared divided by A squared. The integral from 0 to infinity of e to the minus 2r divided by a, 2 because it's been squared, times r squared dr. This integral must equal to 1, and once you do it, you get c naught squared times a divided by 4. This is the integral, equals 1. Solving for c naught, we get c naught to be equal to 2 divided by square root of a. Alright, and the other functions are the associated Legendre functions. Y of 0 and 0 is just nothing but 1 divided by square root of 4 pi. So putting these together, we get psi n equals 1, L equals 0, m equals 0. This function of theta and phi. Psi equals 1 divided by square root of pi times a to the third times e to the minus r divided by a. Okay, here we go. This is the first quantum state for the wave function. This is equation number 33. For n equals 2, we have the ionization energy E2 equals to negative 13.6 divided by 4. That's going to be equal to negative 3.4 electron volt. So this is the first excited state. So the first excited state, n equals 2, L can be equals to 0, right? Or L equals 1. In case of L equals 0, we have m equals 0. In case of L equals 1, we have m can be equals to negative 1, 0, or 1. So it's actually the first, I said the first excited state, but it's actually the first excited states because there are 4 of them. 4 states. Alright, so if L equals 0, the recursion formula number I think 31, the recursion formula gives us C1 equals C naught, right? And C2 give us 0. This is for j equals 0. This is for j equals 1. Okay, so our functions, the polynomials we have equal to C naught times 1 minus rho, right? So now the radial equation, the radial function are n equals 2, L equals 0. is equal to C naught divided by 2a times 1 minus r divided by 2a times e to the minus r divided by 2a, and we have r of 1 and 0, I mean 2 and 1. We have C naught divided by 4a square times r e to the minus r divided by 2a. Okay, so we have these two constants we have to normalize. This is quite tricky. It's not that easy to normalize these two functions. I invite you to do the normalization, okay? If you do the normalization, you should get the first wave function size 2, 0, 0 equals to 1 divided by square root of 2 pi a times 1 divided by 2a times 1 minus r divided by 2a e to the minus r divided by 2a. And the second scenario is L equals 1. We have the wave function to be 1 divided by square root of 6a. This comes from normalization, divided by times 1 divided by 2a squared times r e to the minus r divided by 2a times square root of 3 divided by 4 pi times cosine of theta. There you have it. If you want me to do the normalization, just write me a comment and say you would like to see the normalization for these two quantum states. Let's visit this equation. N equals J max plus L plus 1. And let's take a look at, from this equation we have L must equal to 0, 1, 2, 3 all the way to n minus 1. For each L, we have 2L plus 1 m values. So the total degeneracy of the energy level E sub n is, the total degeneracy is d of n equals the sum of L starting from 0 all the way to n minus 1 of 2L plus 1. And if you remember this series from calculus 2, this is equal to n squared. Polynomial nu of rho, given by the recursion formula, is a very well-known polynomials to applied mathematicians. And these polynomials are given by the following formula. Nu of rho equals L sub n minus L minus 1 to the power of 2L plus 1 of 2 times rho. And these guys are the associated Legendre polynomials. And these guys are given by L sub q minus p to the p power of x. You can rename 2 rho as x, it's the same thing. Is defined as -1 to the p power times a p derivative with respect to x. This p derivative of e to the x times another derivative with respect to x, another q derivative, and this derivative of e to the minus x times x to the q power. So here you're gonna have to take two derivatives. The first one is the q derivative of this quantity, and then after that you're gonna have to take a p derivative for the whole thing. So these are the associated Legendre polynomials, and these gives the solutions for our functions nu of rho. So with this being said, now we finally have our solution, our full solution for the wave function for the Schrodinger equation for the hydrogen atom. As you know, we have psi of n, l, and m, and this psi is given by the two functions r of l and of n and l, it's a function of r, times y of l and m, it's a function of theta and phi. Writing this down, this is the normalized wave function for the Schrodinger equation for the hydrogen atom. First, we have a normalization constant for the radial equation. This is the r piece. We have 2 divided by n a to the third times n minus l minus 1, that's factorial, divided by 2n times n plus 1, that's factorial. We're going to take the third power of that factorial. So this is our normalization constant, and then we have e to the minus r divided by n a. This is the solution for one of the limits for the radial equation, times 2r divided by n a to the l power times the associated Legendre polynomials. We have n minus l minus 1 to the 2l plus 1. This is of 2r divided by n pi. So 2na, these are constants, so the variable here is r, okay? So that's that. These have derivatives, remember, okay? Times epsilon, this comes from normalization for the angle equation, the azimuth equation, times some other normalization constant. We have 2l plus 1 divided by 4 pi times another piece. We have l minus absolute value of m. This is factorial, divided by l plus absolute value of m. That's also factorial. Times the phi solution, which is very simple. It's e to the I m times the angle phi, times the associated Legendre polynomials, p sub l to the m of cosine of theta. Also want to mention that epsilon is equal to minus 1 to the m when m is greater than or equal to 0. and this is equal to 1 when m is less than or equal to 0. There you have it. So this is, let's box it. This is the solution for the Schrodinger equation for the hydrogen atom. This boxed piece. It has a lot of pieces inside these polynomials, but don't let these polynomials scare you. These are just like cosines and sines, or just like x squared plus 4. These are all polynomials. So there you have it. This is the normalized solution for the Schrodinger equation for the hydrogen atom. This is a visualization for the hydrogen wave function in terms of n, L, and m. It gives the ground state and few of the exciting states for the solution for the Schrodinger equation.